Good morning and welcome to day 3 of Expanding Exploration from Vision to Reality, the AAS Von Braun Space Exploration Symposium. Please welcome to the podium, Executive Director of the American Astronautical Society, Jim Way. Oh crap, that's me. Good morning. Hi. Sorry, I just started off a little easy this morning. Welcome to the last day of this symposium. Thank you all very much for being here. Thanks for coming back. We've got a great day lined up. Again, we could not do this without all of our sponsors. So thank you very, very much to L3 Harris, the Aerospace Corporation, Boeing, Lockheed Martin, Northrop Grumman, Amentum, KBR, SpaceX, the University of Alabama in Huntsville, Barrios, Johns Hopkins Applied Physics Laboratory, and Leidos and Teledyne Braun Engineering. Thank you also to our collaborators on this event, NASA Marshall Space Flight Center, the whole team there making this happen, everybody here at the University of Alabama in Huntsville, as well as the National Space Club of Huntsville. We'll hopefully see many of you at the dinner tonight. Just want to reiterate our Q&A process here. So we will have microphones on the aisles, so raise your hand nice and high if you have a question for any one of the panels. And please keep your questions to a question. Nice and short. If you have to take a breath, you're done. So with that, let's get started with our first panel of the day. Please come on up. Don't hesitate to walk right in front of me. Yesterday morning, if you were here, we spoke about the what and the why of nuclear propulsion. Today, we will talk about the how. This session highlights the leading-edge projects and technologies driving the development of nuclear thermal propulsion and nuclear electric propulsion. Our panelists will showcase the next-generation propulsion technologies being designed to push the boundaries of deep space exploration and provide a detailed look at the technical advancements and challenges shaping the future of space travel through nuclear propulsion. Moderating this session is Walt England, Deputy Associate Administrator for Programs in the Space Technology Mission Directorate at NASA. Walt.
All right. Hey, good morning, everyone. Thanks, Jim. Thanks for having us. It's good to be here. I hope many of you were able to see the first panel yesterday. Rayanne Meyer chaired on the same subject of nuclear propulsion. That was a little bit more about the what and the why. I think we're going to focus more on the how, what it is we're doing, some of these specific investments, and how do we keep moving this technology forward. I think I hope everybody agrees. Most everybody agrees this is a critical technology for both human exploration, and we've got some Michael Paul, who's going to talk a little bit about the other applications that we might use for it. So with that, let me introduce the panel. I'm just going to do very brief introductions. They all have long pedigrees, and I could sit here and probably 15 minutes tell you about all the accomplishments, but if you need to know more about them, you can read their bios later, or maybe introduce yourself and chat with them. We're just going to go in alphabetical order. So to my left is Mike Houts. He's a local here at Marshall Space Flight Center. He's a nuclear research manager at Marshall, and we work very closely with Mike and his team on a number of projects. To his left and your right, Russ Joyner from L3 Harris, formerly Aerojet Rocketdyne, principal fellow, propulsion engineer, many decades of experience. Those of you in the community probably know Russ well. To Russ's left, Kate Kelly from BWX Advanced Technologies, Director for Space and Emerging Programs. Michael Paul from the Johns Hopkins Applied Physics Laboratory. Michael is working on the national security space side of things, so brings an interesting perspective, and we might have a few things to say about that. And then finally, down at the end, Todd Sullivan from Lockheed Martin, Director of New Programs, Human Space Exploration. I think we've got a great panel. We're just going to have a conversation. We want to keep it open, and if you have questions, we will certainly have opportunity to take them and have a good dialogue. So with that, I'm going to turn to Mike and let him say a few things about what's going on here at Marshall in the area of space nuclear propulsion.
Morning. Can everybody hear me okay? Or you can at least hear the last two words when I finally figured out where the button was. Okay, so I want to thank everybody for being here this morning. This is a real exciting topic, a real exciting panel. A lot of the reasons I like to just start at a really top level. You know, when we move from chemical to nuclear, what you essentially do is you eliminate all energy density constraints, and you effectively can eliminate all temperature limit constraints. And so it really opens up just a lot of potential. And so a lot of what we'll be talking about today, everything from what we're considering near term to what might be considered further term. We're going to be focused on space nuclear propulsion. Of course, there's also fantastic work going on related to fission surface power. That's being led out of Glenn Research Center. And so again, that'd be for the surface of the moon and Mars. But we'll really be focused on nuclear electric propulsion, nuclear thermal propulsion. And so what I really want to keep in mind is while we're talking about this, we're again, just have tremendous long-term potential in this area. And so, as with a lot of technology areas, the question is always, okay, how do we start? I guess you'd say getting on the curve. You know, start going up the exponential when you're looking at fission systems. And so, we'll have a trade. I think we'll talk a lot about the Draco mission. You know, it's a really excellent partnership between DARPA and NASA. Well, its goal is really just to launch an NTP system, launch a nuclear thermal propulsion system. The U.S. has not launched a reactor since 1965. We did SNAP-10A. The SNAP program was a very, very effective program. Just a lot of benefits from that program. A lot of technologies developed in that program are still useful today. So highly successful, but it's been since 1965. So one idea is just, okay, the U.S., first we need to show that we're still capable of doing everything all the way from the design of the reactor. Kate's probably going to talk about that, I'm guessing. She's at BWXT, they're leading our reactor design. And then, but really just go from the design, then integrating into a spacecraft. We have, of course, Lockheed Martin represented, so a fantastic team. But then, boy, you got to think of little things like transporting and getting to a launch site and integrating with a launch vehicle, and then launching it, and then turning it on in space and taking it up to temperature. And that's part of the where we talk about this kind of whole government, or really beyond that even, but just going through that whole process. And that's, of course, where I look forward to NASA being able to work with NSS and really just to get to it, just to show that we can use these systems. Well, then you move beyond there, then you have people proposing deep space science missions, say with NEP systems, or you have people looking at, we've got at least two companies now saying, hey, they think there's a business case for having orbital tugs. So it'd be cislunar tugs, and that can either be LEO to GEO, again, using the higher efficiency of nuclear propulsion systems. But then once you get into cislunar space, opening that up to the moon, a lot of potential there. Eventually getting to systems with a performance level that we could really help with human Mars missions, and that could be either cargo systems or crewed systems. And again, even those have different requirements, because you think of, okay, a cargo system, okay, I can may take a couple extra months if it just gets me a huge amount of mass there. But a human mission, you might say, hey, I really want to put everything into developing a system that can get me there and back very quickly. And again, that's where sometimes people call like generation 0 and 1 and 2 and 3, but you have this tremendous growth potential with fission technology, so you can credibly talk about 1-year round trips to Mars. Now, that might not be the first human Mars system that we use, but there's some great work going on here, right here at UAH and several other universities, really building on technology that was first proposed in the 60s, developed during the 60s to some extent, but building on that, where those systems are actually looking pretty credible. And I will say, with advances in technology, there's actually been some really clever ideas from these universities that solved some of the problems that they were running into back in the 60s. And that's one advantage that 60 years of technology development and just overall advancement gives you, is you can build on what was done, but you can also apply modern technologies to that. You apply, I guess to say, solve some of the problems that they would have. At the end of their program, they said, okay, this and this and this is what's limiting our performance or causing some issues. Well, now, a lot of areas we've advanced to where we can really resolve those. So just to not take the whole hour, I'll just mention, okay, so two kinds of nuclear propulsion we're talking about. It's all under space nuclear propulsion. First one is just a nuclear thermal rocket. You take a propellant and you run it through a very hot reactor core, and then you expand that propellant out through a nozzle. So it's very straightforward. A lot of times we'll talk to a chemical rocket person. They'll say, oh, that's simple. What's the big deal? Because there's no combustion instability. You only have one propellant. And the little complexity is it's a reactor. Okay, so you have this reactor that's heating your propellant. And so that's, and has to, obviously, the higher temperature you run the reactor at, the more efficient the system becomes. But that's kind of the nuclear thermal propulsion, really short operating time. And we can do a human Mars mission with just a few hours of actual engine on time. But it's trying to run as hot as you possibly can just to make the most efficient use of your propellant. Now, hydrogen, of course, because of its low molecular weight, it's the most efficient propellant, especially for the, I guess we'll call them like the first generation systems. Now, if you develop systems that can run several hundred degrees hotter than those first generation systems, you actually start getting good efficiency with propellants like methane or ammonia or even water. And so that's another advantage of fission is you don't need a chemical reaction to make it work. You can use anything you want to for a propellant because all of your energy is coming from fission. And so with the NTP, probably the early systems will try to stay with hydrogen, but some of the more advanced systems, especially if we're really moving around the solar system, trying to use volatiles that we might be able to access throughout the solar system, you can design engines that can run on essentially any volatile we want them to. And so that's, again, it's fun. One of the great professors here, I won't name Dale Thomas's name, but he always says what's great about this area is there's an unlimited number of PhD dissertations, and so it's because you can a lot of different ways you can go with this. So that's the nuclear thermal propulsion, and then with nuclear electric propulsion, it's the same idea. You're using fission energy to accelerate a propellant, but there you use the reactor to generate electricity, and then that electricity is used to power an electric thruster. And so, again, we can, early systems will probably use ion and Hall thrusters, and then when we get to more advanced systems, you can use more advanced thrusters. You can also run reactors that are, in this case, it's rather than the exhaust temperature that's kind of the key metric, it comes down to your kilograms of propulsion system mass divided by kilowatts that you actually get into the propellant. Okay, and so you have so there you have incentives to make the reactor lighter. A lot of times to make the power supply lighter, that means that you have to run hotter to get the radiator mass down. So it's kind of a lot of good engineering challenges there, but again, a lot of potential with NEP. But even with pretty I always hate using the term existing technology, but what people would consider very near-term technology, we can do some really exciting deep space science missions with a nuclear electric propulsion and start kind of getting a glimpse at what we might do for at least a Mars cargo mission. And then, okay, that wasn't the laser. Oh, there we go. To get the next slide. I was afraid I'd hit somebody with a laser just then, but okay. And so when we just look at applications again, it really is everything from moving around in LEO to GEO, moving around in cislunar space, moving on out to Mars, where you can do a combination of either cargo missions or again the very try to do rapid round-trip human Mars missions, or at least rapid transit missions, or preferably be able to do both, and then really go out into the solar system and with systems that can either indirectly or directly use the resources that we'll be able to find throughout the solar system, Moon, Mars, and beyond. So that I'll turn over to the next person. All right, there you go.
Russ.
That's the laser.
Thanks, Mike. I guess that means I don't have to explain what NTP and NEP are now. You've done that for me.
Advantage of going
And thanks to the committee for the opportunity to be here, and L3 Harris to give me a chance to be part of the conversation, intelligent use of nuclear in space. I'm not going to stay on this chart too long. I just want you to look at the emphasis on the key things of those 6 bullets that are there of what nuclear does for us, and basically how it enables us to put humanity throughout the solar system. And what we want to do with space nuclear is aim to enhance our leadership and capabilities as a spacefaring nation and civilization. So kind of stick that in your head and walk away from this panel meeting with that as a bottom line of what we're really trying to do here. And I'll move along. Also, this is what I want you to go away with too, is a vision as you look at this chart and go from left to right. That's kind of the left side is the near term, what we can do. And it's the sustained lunar ops. It's the integrated use of Earth to orbit, low lunar orbit operations, lunar surface operations, our capabilities that are beyond anything that we did in Apollo, that we thought we would do after Apollo maybe. But now we've got a new opportunity, and we need to make those steps and go forward. You can then see kind of after lunar, maybe what we start looking about is AI-enabled, AI-controlled, not command, of nuclear space systems that act as sentinels. And you can take the little pun if any of you recognize some of that in the cartoon there, what I'm talking about. And then you can actually see the capabilities that this will have in that first left-hand side of that chart, where we're using nuclear thermal propulsion for rapid trips to the moon, 24, 48 hours, depending whether your lock's augmented or not. And then basically being able to support either common operations for crew, rapid crew, and then maybe essential items that need to be like FedEx kind of approaching your mentality up to our lunar operations facilities. And also the thing about this too is this gives you a chance with nuclear, whether it's, we're talking fission to keep everybody warm down there in the South Pole, or we're talking about radioisotope thermal generators, where basically I need to survive the night in rovers. They gotta be able to sustain themselves, whether they got a garage to park in or whether they're sitting out in the open. So then as we grow in knowledge and operational capability, you can see as we move to the right-hand side there, we start moving on to Mars. You can see we have operations on the Mars surface. And then sustainability means of interacting between Earth orbit, lunar orbit, Mars orbit, and down to the systems that need to be operated around Mars, both nuclear thermal, nuclear electric, where nuclear electric provides a lot of opportunities when you grow it to be able to provide a self-sustained depot in space that serves many areas, which allows us to continue on to the deep part of the solar system and the outer planets, the gas giants, the ice giants, where basically the Mars then becomes the second stepping stone. If we're thinking of moon as the first one, Mars is the second for sustainability of humanity's exploration throughout the entire solar system. That's what I want you to think about, because the end point there, it was mentioned yesterday, and I thought it was a good way to think about it, is that AI-enabled, which is AI control, could actually, with like the uniquely sized, optimized nuclear electric propulsion approach, could permit round trips to the outer planets. You can imagine a sample return coming back from Uranus or Neptune. Now, those are long distances, so it's not going to happen overnight where you're going to go in and come back. But it surely could provide a first opportunity for a round trip of sample returns from some of the moons that are there, even beyond what we're thinking of looking at with Europa Clipper now. So I want you to ponder this new world, this new future that basically building this world of tomorrow becomes off of space nuclear propulsion and power. You ready?
How about down to Kate?
Thanks, Russ. Thanks, Mike. Making my job much easier. So I'm going to focus on the perspectives on advances that have been made from a nuclear industry perspective to help enable these future propulsion technologies. So BWXT is, we're newer to space. We're primarily known as a manufacturing and technology company for our work over the last 7 decades to deliver the fuel, nuclear reactors, and plant components for the U.S. Navy's submarine and aircraft carrier fleet. Around 2017, there was this renewed interest in the U.S. government to look at how they could use nuclear technology in new places that are being used currently. That created or fostered the start of the division that I'm representing today, which is Advanced Technologies. And today, it looks very different than when we started 7 years ago, but our 3 focus areas are all looking to harness the same benefits of nuclear energy. So trying to use the efficiency and resiliency that nuclear can provide to give us access to and sustain activities in places that we currently can't reach or are very hard to reach. 2 of those 3 areas, so the one on the left and the one on the right, are focused on Earth, so deploying microreactors. There's been a lot of news recently about small modular reactors and some significant investment from tech companies to help move this critical technology forward. What we're focusing on is a little bit different. Microreactors are a type of super small, factory-built, and readily deployable nuclear plant to provide power for remote operating bases and can decarbonize remote industrial processes. The third area of focus that we have is the space portfolio, which is the portfolio that I lead. Collectively, these three domains where we're progressing nuclear technology has been part of this broad interest and this incredible momentum in nuclear. And it's one of, believe it or not, one of the key advances that's enabling the deployment of these systems in space. So it's fostered more competition, which has fostered more innovation. It's establishing a stronger supply chain. It's instilling an influx of investment to create new infrastructure and new capability. It's built a strong stakeholder advocacy outside of the nuclear industry, across government, across other stakeholders. And it's brought more diverse and more innovative talent to the industry, and all of these attributes are needed to solve the remaining challenges that remain and push space nuclear technology forward. So shifting to the space portfolio specifically, there's been a lot of activity. Some of it's been touched on today. BWXT is participating in parts of that development. We have work with NASA on their fission surface power pursuits. We have a collaboration with the UK Space Agency and Rolls-Royce Submarines Limited to develop an alternate concept for fission surface power. We're participating in a program called the JETSON program with the Air Force Research Lab. That was a topic of conversation yesterday during the nuclear panel as well, which is working to demonstrate and develop nuclear electric propulsion technology for operational use. And then last, there's DRACO, which is going to be the biggest focus area for me, and it's certainly received a lot of attention over the last couple of years, and it's a really exciting program that's going on in industry. So the picture of the bottom is of DRACO concept with our partners Lockheed Martin on that activity. Hopefully you've seen that picture before because it's, I think, a really exciting one, and it marks a lot of the progress that's been made in the industry. So the fact that, now switching to my last slide to talk about DRACO a little bit more. So the fact that we as a country and a community are committed to DRACO and pursuing DRACO is a huge step forward, as Russ had indicated also, in our readiness to deploy space nuclear technology. There's been a lot of advances that have been made for us to be at this point, and a number of advances that will be accomplished through execution of the program. So DRACO will be a flight test of nuclear thermal propulsion technology in the next couple of years. BWXT's part of that is delivering the fuel and reactor and performing the associated design and development activities that are needed to get to that point. An NTP system, the reactor itself is operating under extremely harsh, difficult conditions. So the system has to survive the dynamic launch loads. We have to survive a number of different operational scenarios. The temperature inside the system can exceed 2,500 to 3,000 K, and you're using a cryogenic propellant. So extreme conditions, kind of on all ends of the spectrum, that we have to design and develop a system that can survive. We've made several key advances in our ability to manufacture these high-temperature materials, specifically the high-temperature fuels, to give us confidence that we can survive under these harsh conditions. And we're performing a number of key development activities with our partners to buy down the remaining risks to make this project feasible to complete in the next couple years. The program itself is going to pave the way through a number of areas to enable a future where we have multiple types of nuclear systems operating in space. We'll navigate our launch and regulatory process for the first time. We'll establish the contractual basis that's needed to be able to receive, transport, handle, deploy these nuclear systems, but we'll also buy down a number of technical and integration risks that help enable that future. So a colleague of mine said recently that, nuclear is hard. We all know space is hard in this audience, and you put them together and it's extra hard. May have been said more eloquently than that. But so DRACO will take a nuclear subsystem that's developed by a company with its own set of culture, its own set of standard requirements, and pair that with aerospace components to integrate the full system with the space requirements, their own set of technical challenges and our own respective languages, if you will. We'll break down those barriers to be able to deliver the system and deploy it. And one of the keys to being able to do that, not just buying down that technical risk, but it's establishing the partnerships that help move that forward. So we've talked about the partnership between DARPA and NASA. That's a big part of that, but then our industry partnerships as well, specifically with Lockheed Martin to help move that forward. Through Draco, we'll be able to address those issues. All of the space nuclear pursuits that we've touched on will be the beneficiary of that, and it'll be a step towards the future that I have shown on this slide. A very exciting one that we believe is certainly achievable. With all of this momentum that we can maintain. And that future looks like providing milliwatts to megawatts of power on orbit, whether that's power on the surface of the moon, power for on-orbit spacecraft operations, and then enhanced propulsion capability, whether it's for cislunar transportation or eventually to be able to send humans to Mars. So, thank you.
Thanks, Kate. Michael, bring us a little national security space perspective to the extent that you can in an open forum.
Thank you. And thank you all for having me here. I'd like to propose 2 ideas today. I don't have any slides for you. Any background is fine, but thank you. But before I do, I feel like I should give you some context on why I believe in what I'm going to share, why I think these 2 ideas are worthy of discussion. And I want to say from the outset that I think that these ideas may make me the least popular person on this panel, and I'm sitting between 2 folks here who are doing great work, so I've just made sure I know where the exits are. All right. A mission that I got to work on that was transformational for me was the Mercury Surface Space Environment Geochemistry and Ranging mission, the worst, most convoluted backronym in NASA history, the MESSENGER mission to Mercury. It was a discovery mission that launched in 2004. And so America had sent a spacecraft to Mercury already. In 1974, Mariner 10 was launched. It flew past Mercury 3 times and opened up a window into so many different questions that we had no way of answering about this puzzle piece in our solar system that we needed an orbiter to go back and do it again. And so for 30 years, the scientists hoped for the funding for that mission, but they also hoped for the funding for the technology development to enable that mission. Because the premise was, in order to orbit Mercury, you were going to have high temperature avionics that would survive in that hot, hot place. And Mariner had just passed through, but Mercury, as an orbital mission, you would have to set up shop and stay for a long time. And so for 30 years, the funding to develop those high temperature electronics came and went. There was some progress and some setbacks, and for 30 years, there was no new progress there. We did not actually get to where we needed to be. And then, in the late 90s, a team proposed that instead of all of that investment and running at high temperatures, we simply send run-of-the-mill avionics on a fairly run-of-the-mill spacecraft to go orbit Mercury behind a great big beach umbrella. Well, it wasn't exactly a beach umbrella. It was high-quality, high-temperature ceramic cloth made of the same material that protected the space shuttle while it comes in for re-entry. It hung off a titanium frame on the front of the spacecraft, and it allowed MESSENGER to run at about 20 degrees Celsius, like room temperature, for all of its orbital mission. There were other innovations that enabled MESSENGER, such as the high delta V biprop system provided by Aerojet. Thank you, Joe Cassidy. There were a lot of things that came together to make it work, including a very high reliability, a very protective, a very finicky software system that checked the sun angles about 15 billion times over the course of the mission to make sure that that sunshade stayed there between it and the spacecraft, so that between the sun and the spacecraft, so that it would not overheat. And if it got out, if it lost its mind for a minute and accidentally pointed in the wrong direction, it'd be dead in like 5 to 10 minutes, just completely dead. This might not sound too crazy because now we have Parker Solar Probe getting into the corona of the sun, but APL first built and flew Mercury's mission, MESSENGER, and now we're flying Parker Solar Probe, and so there's some good progression there. MESSENGER was a huge success, but it was also a great model for breaking down decades-long barriers to progress. And Mike pointed out that we haven't launched a nuclear reactor since 65. Thank you. So we know what decades-long delays in progress look like, don't we? Messenger succeeded because Mercury had become a high priority for a focused and influential set of stakeholders. Messenger succeeded because we built on the investments made by other communities, the reentry community, the shuttle program, and we didn't have to start from scratch to get to the place where we had something that would work. So today I'd like to propose two things, and you've perhaps heard the phrase that history doesn't repeat itself, but it does rhyme. So I feel like in some ways that experience rhymes with where we are today. In the resource-constrained environment that we're in today, I propose that we talk about focusing on prioritizing what mission we do first. And it's a mission that has to serve as a demonstration that we can build space nuclear reactors and put them into space, and that we can safely and responsibly use nuclear technology in space. We are a leader for the world when it comes to space exploration and technology and use. And this is an area where I think it is a critical moment when we do that. Show what safe and responsible use of space looks like, nuclear in space looks like. I think that this needs to be a tool for a focused and an influential set of stakeholders, and I propose that it uses an electric power generating fission reactor at its core. It gets launched directly into a nuclear safe orbit around the Earth. That's idea one. Idea two is I propose that we separate the variables like good algebra students. We have N, E, and P all in this equation that we've been carrying around for so long. And I think that the P needs to be separated out. Because the propulsion, the electric propulsion systems that we talk about, they can use electricity from other sources like solar panels. And they have had decades worth of commercial space flight with great success, and more advanced higher thrust electric propulsion systems are coming online. And when we do this, when we say NEP, we take the really hard part of nuclear and space and the really hard part of higher thrust nuclear propulsion, and we glom them all into one program, and we defocus from what I think is the most important part of it, which is the N, the nuclear. So I believe that only through focusing on this reactor question and getting through that barrier of progress can we break away from not a 30-year cycle, but a 60-year cycle of technology starts and stops and billions of dollars spent with no new reactors in space. Thank you.
Thank you, Michael. And how about Todd from the Lockheed Martin industry perspective?
Okay, thank you. And going last, I get the benefit of being able to build on all the comments that my panelists have already made. So at Lockheed Martin, we are mission partners to our government customers. And we work with those customers to look ahead at their needs for the future and develop space architectures that will deliver on those needs. At the same time, we evaluate the efficacy of new technologies, emerging technologies, on how they can enable or enhance those architectures and provide capabilities that aren't otherwise available or available today. And nuclear fission is one of those key enabling technologies that is ubiquitous across all of our mission domains and our customers, whether it be national security space, human space exploration, planetary science exploration. We find the value of fission reactors to be transformational in all of those domain spaces. And so we've been partnering with other industry partners like VBSES and with the government here over the last several years to develop the critical technologies necessary to field nuclear-powered systems. And we are looking at and participating in programs in all three areas: nuclear thermal propulsion, nuclear electric propulsion, fission surface power, and electrical power in space. And we're investing in the technology development that serve all three of those potential applications. And in our architecture studies, it's clear that there are advantages for one style of nuclear technology versus another. For deep space missions where you have a long time to get there, you can see the real benefit of in EP. For missions which are time domain sensitive, NTP is certainly preferential. So there are cases in which each of those technology types really are valuable. There's some technologies that, and technologies and approaches, I should say, that are applicable to all three of those applications. And so while we're partnering with industry partners like VBSES to develop their reactors, and Kate spent some time talking about the plans and progresses that have been made here in the reactor area, I'll talk about all the other technologies necessary to convert that fission reactor into a usable propulsion system or spacecraft. One of the most important pieces is the engine instrumentation and controls. So at Lockheed Martin, we have been providing control schemes and control equipment for commercial power plants, commercial nuclear power plants, and nuclear Navy power plants for several decades now. We're taking what we've learned in those industries and utilizing them to develop control schemes, autonomous control schemes, that can start up and operate the reactors and shut them down autonomously in flight. And so over the last couple of years, we've built the modeling and sim tools to model both the reactor and propulsion systems and fission surface power systems, and to incorporate various control schemes and evaluate their robustness against all of the things that we might find in space, dispersions or uncertainties, for example, be able to trim the reactors and optimize control schemes in space. And the Draco program will flight demonstrate the utilization of those control schemes. The next topic comes down to test. So in the space environment, we typically take spacecraft through a development phase, then a qualification, and finally a certification or acceptance test phase, where each of those phases have different purposes. Ultimately, we certify a system is ready for flight by exposing the entire system, component level and system level, to its functional requirements and verifying the functional requirements, then exposing that spacecraft to space environments all the way through a campaign that is test like you fly. So not only the environments, but the sequence of those environments, and then ultimately we do a functional test at the end to verify that the spacecraft survived those environments and functions as intended. But that's really difficult to do with a fission propulsion system. There are limitations in the facilities and in the licensings available to us today to enable us to do a full end-to-end system-level test and exposure to environments. And so one of the real challenges that we're focused on over this year and last year is teasing apart the requirements that must be verified, the test approaches that we'll utilize to verify those requirements, and to ensure that we've got an effective system and a safe system before we launch. And that's applicable to the things we're learning today and how we're developing our test strategies and certification strategies. That's, again, useful for NEP, NTP, and for fission surface power as well. And maybe the last comment has to do with cryogenics. So, Mike, you talked about utilizing propellants, a wide range of propellants in fusion reactors. But the one propellant that provides you the best efficiency due to its low molecular weight is hydrogen. It's also available in situ throughout the solar system in the form of ice. And so refueling a hydrogen-fueled fission reactor or fission power plant is possible, enabling some missions that we can't do today because you can refuel from in situ propellant sources where you are visiting. And so demonstration of the cryogenic technologies for this sort of mission requires zero boil-off or very low boil-off technologies. That includes passive and active cooling systems, isolation, insulation, and cooling systems. And over the last several years, we partnered with NASA to do some demonstrations in cryofluid management. So as part of Next Step Appendix N, last year we completed a large-scale cryogenic demonstration where we took a stage-scale tank, applied the passive cryofluid management technologies such as very low conductivity struts, low emissive blankets and tube-on tank cooling systems, and conducted a large-scale test of that stage. We've also developed fluid transfer mechanisms to be able to refuel on orbit the hydrogen propellant. And the reactors themselves have the energy to be able to do multiple missions and refuel just the propellant. We're working now on demonstrating those technologies in flight with a proposed cryo demonstration mission, and then ultimately on the SLD program, the Sustaining Lunar Development Program. With that swim lane of technologies, coupled with the technologies that are being developed on the Draco program and Jetson programs, we'll be able to build a operational stage capable of doing the interplanetary transport or the lunar cycling that you talked about earlier. So those are three examples of technologies that apply ubiquitously across all of those applications and will serve to enable some of the architectures that Russ, you showed on your slide. Okay, I think with that, we'll hand it back to you, Walt.
That's great. Hey, thanks. Let's see. I've got a list of questions, but I think in the interest of time, I'm just going to open it up to the floor and see if we've got questions for the panelists. So it looks like we've got mics, and first question.
Hi, thank you for the great panel and the great discussion on these technologies. My question was following up on what Michael said. What divestments and distinctions need to be made to ensure the success and reproductions of NTRs at the commercial and civil level?
Did you say of NT
Neutral thermal reactors.
rockets? Thank you. What are the investments that need to be made?
Yeah.
I know less about that than most of the people on this panel, but I'll give you my short answer, and it's first the fuel, and second, it's the rocket itself. I mean, the rocket engine needs a lot of testing, and we spent $6 billion testing rockets exactly like that back in the NERVA rover program, and still don't have any to fly today. So there's a lot of investment to be made. And those were 1950s and $60, so I don't even know what it translates to today.
And I'll also add, and Kate knows this, and I know for sure Mike, it's not just the fuel. In this case with HALEU, you got to be looking at the moderator, because those highly moderated configurations on the core, we need to be testing, those higher temperature conditions with coupled moderator for sure. And don't forget the non-nuclear pieces. If you're talking right now, Draco is a not using dynamic pump-fed systems directly. So if you're going to have a fully operational system using cryogenics, you're going to want to be pump-fed. And you're going to want to be able to have a coupled control between the non-nuclear propellant delivery system and the reactor. That's going to be a key thing you want to test, is that rotating turbo machinery that's going to have to run for 10 minutes, 20 minutes per burn, and you got multiple burns. So there are things you can test with that right now and promote that technology without even having it on a nuclear reactor, and ensure you got high operability on those sort of systems as you move from Gen 0, Draco, to Gen 1 and Gen 2.
Yeah, that's exactly right. And some of the underlying challenges that have to be explored for that turbo machinery have to do with materials and the tolerance of those materials to the radiation environment. So we have a long history of turbo pumps and electric-driven boost pumps. We have a long history of cryogenic valves, but we don't have a long history of those components in a nuclear or in a radiation environment. And there are some components within those turbo pumps and in those valves that are susceptible to radiation degradation. So there's some material testing to go along with what you're describing as well.
Yeah, and I think right now you can go to say the longest running in-space propulsion system with LOX, or in this case hydrogen, is RL-10 for the number of burn times, and then you go RS-25. But they're the knowledge we got, and they've not run this long a time. And don't forget valves. You got to have valves that cycle quite a few times, and they got to be low to no leak, low leak, so when you're doing cryo there.
Yeah, and I think what's being touched on here, which is great, is one of the things, it has been almost 60 years since the Rover Nerva program, certainly over 50, and we really need to be focused on the advancement degree of difficulty. In other words, looking at what we have now, the test facilities we have, the possibility that we'll be doing a in-flight, an in-space demonstration, and then what's the best way to get to an operational system, and by best 80 squared, that's advancement degree of difficulty. And so I think for a while we've been kind of hung up on technology readiness level, and it finally dawned on people that the Saturn V by definition is a TRL-9 because it flew in space, but it'd be really hard to build one right now. And so likewise, rather than going back to the Rover Nerva program, people are looking at, okay, what do we have now? What are our test capabilities, experience related to small modular reactors across the nuclear industry, but valves and pumps, everything. How to package that together, and that's the good news is, again, what's been so important about having industry involved is we've got some great ideas, and again, there's at least 2 companies out there that have, they feel they have a very strong business case for their first operational space nuclear propulsion system. They both happen to be NTP, but I agree there's also a lot of good applications for NEP systems also.
And yeah, I was going to say, good segue, NEP, because we got areas there we got to address too. I mean, high burn up, HALEU fuel for a power core, that's, in a moderated power core, that's definitely one thing in the list, as well as the aspect of running, if it's a Brayton unit, you got to have a Brayton unit that's got to basically run way beyond what we've tested them at. Done real good with Stirlings, but we haven't really tested Brayton units space capable to run for months, years, and we need that sort of capability to test those. We want to apply them in different areas like FSP or nuclear electric propulsion. And, don't forget the radiators. We need radiators, and we got to have a way to test those at the size and then the coupled form that we're going to have to launch them and then have them be available to get rid of all that inefficiency from the power conversion system. And they got to be tested relative to launch loads because you kind of make them in pretty lightweight stuff. So those are key things we got to be dealing with in both the 2, NEP and NTP.
I'll add to your comment about radiators. They constitute about 60% of the mass of the power conversion system. And so while fundamentally simple, they represent a large proportion of that system. And so lightweight radiators that can survive the environments and then be deployed and then work reliably over a period of time, be not susceptible to MMOD strikes, for example, are an important technology advancement that needs to be addressed. And then the power, you mentioned Braden cycles, operating those cycles or operating those tiny turbomachinery components at very, very high temperatures so that you can get efficient radiators is also an important step.
I was waiting for Kate to jump in and talk about high voltage power management systems, because what we're talking about, we're trying to feed off of other areas, but high voltage power management's another one too.
Are you prompting me?
Kate, you want to comment
Right.
on that?
Yeah. So if I think about investments that have been made, a few things come to mind immediately. So first, there's been a pretty healthy amount of investment by NASA made over the last 7 years to help us get to the point where we're at today. And that investment focused on high temperature materials and testing at a subcomponent level to buy down the key risks in the system. BWXT and I imagine others in industry also made kind of their own parallel investment, and ours wasn't significant to help further address those risks to get to the point where we can confidently move to the flight demo of an NTR in the near future. The last piece of significant investment we made were in facilities. So a lot of the facilities that are in the nuclear industry were built in the 60s timeframe for a number of reasons. The Nerva rover program was one of them. Some terrestrial and naval applications were another. So there hasn't been a lot of new nuclear facilities that have come online, either for testing, manufacturing, or even operations in the last 50, 60 years. And so we've done that to help prepare for this future that we see, both on Earth and in space. And those investments, while focused on NTRs, have been pretty transferable to talking about these NEP systems as well, at least on the nuclear side. So we benefit from the fuel and manufacturing perspective, we benefit from the infrastructure, but then for NEP systems, there's a ton of overlap and similarity between how the nuclear reactor is designed and needs to operate for a in-space system compared to these terrestrial microreactors that we've talked about. So a lot that we can learn in those areas as well.
And actually, if I might add, Kate, you mentioned earlier the path that you all are working on in terms of getting regulation and process in place so that everything can come together at the launch site at the right time, in the right place, safely and securely. And I don't know how many of you have been a part of a program that has integrated a radioisotope power system onto a spacecraft, but for the New Horizons mission, right, there was this Pathfinder program where between the DOE and APL and folks from NASA and down at the Cape, we went through this process of building mock-ups of the radioisotope power system. This is how it's always done. This isn't special to New Horizons, but for those of you who don't know, you basically go through all of the orchestrated steps of what does it mean when the spacecraft gets to the Cape and the RTG gets to the Cape, and so that the people who are close to the radioisotope material are there for as little time as possible. And they go through practice runs and dry runs and dress rehearsals over and over and over again in order to make sure that when that happens, there are no anomalies with a nuclear reactor or nuclear power source at the launch site. And it takes years to plan this. It's going on for Dragonfly right now, which doesn't launch for years. And on New Horizons, adjusted to, I did check this one, adjusted to today's dollars, between that effort and the NEPA paperwork for the launch of New Horizons, DOE spent $100 million just on that process. And it's a well understood process. We do not have this process for fission systems right now. And so what Kate was talking about is critical to getting anything to the launch pad in the future.
Yeah, and I will just add the NSPM 20, which was referred to some yesterday, that's a huge step forward because it gives us a quantitative measure to strive for. And then also we do have a lot of
Quantitative, which quanta are you measuring?
Okay, so quantitative because, okay, I'll digress. So I worked the Flight Topaz program. That was back in the 90s, and we were working, in that case, it was with the Russians to fly a Russian reactor. And we started looking at, okay, how are we going to launch this? Okay, well, you want it to be safe, okay? So then there was no quantitative definition of safe. And so we literally came up with the most, I'll just say, ludicrous scenarios that even if they had occurred would not have posed any dose risk to the public. What NSPM 20 does is it says, no, you have to demonstrate, and this will be the key. How do you demonstrate that? That there's, you are below a certain probability of giving an individual a certain dose, or a certain dose range, or a certain dose or above. And so, so it's very straightforward to meet those criteria. And it took several years to develop that. NSPM 20 was signed by at least 7 agencies. That's why it took several years. The president signed off on it. And so, so this is our opportunity. But it's very, again, very consistent within our CEPA regulations. And so, but before then, it was not quantified for reactors. And that was a huge reason why we weren't able to launch a reactor since 1965. That has changed, and it's
and so that adds clarity
to our benefit. Yeah.
But it doesn't relieve the launch safety engineers
and
everybody else from all of the work that has to get done and the hundreds of millions of dollars that need to get spent just on saying, yes, it's okay to launch.
Yeah, and that will be, we need to make sure it is safe when we launch it. But, we have so many reactors running. We have reactors running at universities. We have criticality experiments that are routinely done. We've not had a significant criticality accident in the U.S. since the 60s, so we know how to work with reactors on the ground. And what NSPM 20 does is, of course,
but we have no reactors at Cape Canaveral right now.
We don't, yeah.
And that's a big hurdle to get over.
But I will say, though, there are dozens of reactors across the U.S. that we can draw on that experience.
Yes.
There are dozens of RTGs across the U.S. that we can draw on that experience. So it's a little apples and oranges, but we have a lot of experience in this area that we can, but we need to. So agreeing with you, we absolutely need to get that transferred to the launch facility.
And this is why
but we have that experience. We have the people that are working in that field now.
This is why we need that focused and influential stakeholder set to make sure that all of those monies are available. Kate, you were going to say something. I stepped on you. I'm
Oh,
sorry.
it's okay. I was, thought maybe we'd want to ask another question.
Yeah, the interest of
But
time.
I was
Yeah.
just
Yeah,
going to
second thoughts now.
emphasize the importance of Draco in executing and working through those problems, because yes, we haven't navigated this before, but that doesn't preclude the fact that we aren't ready to go through those actions because of, I mean, there has been significant change in the amount of stakeholder advocacy and, you know, supporters of moving this forward, not just for Draco, but for nuclear in general.
And I may have one last point to complement your point and yours, is that basically until you have a design that you can walk through that process, you really don't have anything to process. RTGs, we understand them, we've flown them, we have something that we walk through the process. Draco gives us a design to walk through that process.
Yes.
that
This
you
is
can-
like Ghosts
you
of
can
Admiral
quantify
Rickover.
things with.
I would say we probably need to get the hook out. Clearly, there's a lot of energy in this topic. Thank you to the panelists. Thank you to you all. If you have other questions, hopefully our panelists will be around and you can corner them and ask them for more opinions.
I don't want to shortchange you. You know, we got started with you a couple minutes late. Do you have time for maybe one more?
Oh, we could go all day,
All
Jim.
right, so let's do, that's a good problem to have. Let's do two more quick questions, okay?
Okay.
So we
You
got
want to do it from the audience?
quick question with relatively quick answers?
Yeah, hi, my question's going to be for Mike and Todd. So in the 60s and 70s for Rover Nerva, obviously they had a giant ground test campaign for the rocket engines there. So, and from what I know right now, Draco does not have any plans for ground testing due to regulatory issues. So my question's going to be, do you guys see essentially any future in in-atmosphere testing and on-ground testing of nuclear thermal rocket propulsion systems? Thank
Yeah,
you.
I'll just jump in real quick. So we actually do have a lot of testing that's going on. We're doing fuels testing, both non-nuclear at temperature. We're doing fuels testing in reactors. We have some tests at the MIT reactor. We talk about some tests at the Idaho National Laboratory. There's other facilities. So there is a lot of testing, but the key is just, both nuclear and non-nuclear on the ground. And one of the benefits of Draco is from that flight, we will then see, okay, what additional ground test capabilities will we need? But I think we're very confident with the combination of in-space and ground testing that we'll be able to field operational systems. I'll let
Yeah, thanks, Mike. That's essentially how I would have answered the question, too. There's a tremendous amount of development testing, qualification acceptance testing planned. But the purpose of the Draco program is to conduct the sequence of tests in space that we can't otherwise accomplish on the ground and collect the data necessary for future operational system designs.
I want to add one point on this. I think I'd like to see coming out of the Draco a national strategy for testing, somewhere where we have a facility that are multiple clustered, supporting a major area where we can do ground testing in different categories that allows us to do integrated testing at certain levels. We need a national strategy, and as you say, every areas that need to be funded, and that's one area that seems to be weak in funding, is to allow us that capability to have throughput.
Okay, and the last, since Russ wasn't asked and he answered, I'm going to also. The last thing I'd note there is that, they're exactly right. We're not testing a fully integrated engine on the ground for the first time, but we are doing a lot of other testing at the component level, at the subsystem level, that's highly relevant. And there are plenty of other examples in aerospace where we aren't testing the full system, operating it until we're in space for the first time. So this is certainly a problem that we can solve.
Jim, one more?
Yeah, I just have a dumb guy question with respect to nuclear electric propulsion. Just looking at the advances we've made in things like lasers and LEDs as more of a direct energy conversion, is there no scientific or other phenomenon out there that allows us to do something besides just use a fission stockpile to drive a steam turbine for electric nuclear propulsion out there?
Yeah, all kinds of advanced technologies that can be applied for the, NTP and NEP. But yeah, we can do with nuclear electric propulsion, many ways proposed for converting the fission energy into electricity, and many ways of then using that electricity to drive a thruster. And it's really looking at that integrated system so we can get the kilograms of the propulsion system, mass per kilowatt that actually goes into the propellant. Want to get that as low as possible. And so there's some people that they're looking at advanced systems. They're saying we can do a round-trip human Mars mission in like 210, 220 days. So I mean, so it's now it's really advanced, but so you're absolutely right. We're definitely moving away from the steam turbine. It does great, but we're moving away from that and got a lot of other technologies.
Okay. All right. Thanks to the panelists. Thanks to you all. Jim?
Thank you
Back
so
to
much.
you.
Yeah, thanks everybody.
Thank you so much.